we have our Cocoa class, the number of classes that we have in the Cocoa dataset. There are exactly 80 classes available in Cocoa dataset, like person, bicycle, car, motorboy, and so on. And I will have image example of a living room or another sample example of this car that we will use for our test purpose. So for the coding purpose, you don't really need to install anything. All you need to do is to just import the provided widths and configuration files into the OpenCV. There are some constants I use for my code. I'll just go through all of them quickly so that you'll understand it, and then we will skip this part of the code and jump into how to really use the YOLOv3. We import our modules, CV2 and NumPy. We have a Windows name for previewing the images, and in order to import the CNN model into your project, you would utilize the DNN module of CV2. So in the DNN you have a function called readnet, which is basically reading the network into your project. We'll provide the readnet with two parameters, which is the model weight and the configuration files. Then we open up the Cocoa dataset, and then we store all these classes into an array. To show the number of classes or classes, you can basically print it on top of bounding boxes. Like if we detect a bounding box of a person, then we want to write person, so that's just the font for that. And the colors are the bounding box colors that we will use, or the font colors that we can use for our objects that has been detected by YOLOv3. So in here we use the 80 colors, assuming that if in an image there are 80 objects, all these objects that has been listed by Cocoa dataset has been detected. We just use the length of this 80 classes and then generate that many colors. And this is just another flag that we will use to whether visualize our image or not, so it's acting like a switch. You will have your own coding style. Everyone coding style could be different. I'll just use it as a flag, so for me it's easy to switch it on and off whenever I need it. We'll load our image, and then we can see how to we will get the image height and width and the channels. We will need them in order to denormalize the bounding box values. To show our image, we use this Windows name, the debug is true, and then we want to visualize it and destroy all the windows when we press the key. Let's visualize the image and see what kind of image do we have. To do that, we run this and see. So here is our image. We have an image of a person, a number of cars, some traffic lights, building, and so on. So the purpose is to find like car is an object, how many cars are there, and where is the person, and whether the model would be able to detect the flowers and the bicycle and so on. So we get the layers. If you would like to know what are the layer names, it's actually showing you the structure of the model. So we can print the structure of the model by get layer names. If we print that out on the screen, we will see something like this. Yeah, so as you can see in here, this is the layers of the YOLOv3. We have the convolution layer, batch normalization, leaky activation function, and so on. So this is the whole structure of how the YOLOv3 is architected. If you want to know details about YOLOv3, I again encourage you to go for the paper, at least go through it and skip it and see how does it work. But for this coding, you don't really need to understand the theory behind that. We just use it in practical. How does it detect objects? So then we want to get the output layers, and then we want to pass this output layer to feed forward. In the output layer, we want to, once we forward the image into the input layer, we want to get it to the output. So we will use that. For any neural network, we have something called blobs. We gotta get the blob of the object. Well, basically, blob of an object is nothing but separating all these three channels like RGB into a separate and different images, like three different images. To do that, we again have a utility function available in cv2.dnn.module. We have something called blob from image. We pass our original image in here, and then we have a scale factor where we can use that. For this, I found that the scale factor is 0.00392, and then we have the size. In here, size refers to the input size for the model, which is 416 by 416 for YOLOv3 model. And then we have the mean, which is 0 in our case. YOLOv3 is not using any mean. And then we have another flag called swap RB. Basically means, would you like to swap the red channel with the blue channel? Oops. RB. And we keep that true because OpenCV reads image in BGR format, and for the model we need to swap that to RGB. And then there is another flag called crop, and we set that to false. So if you would like to know what does blob really works, let's just visualize the output. We come to the debug part and say for B in blob, and for image, or we can say blob I and blob image, and enumerate B enumerate V, then visualize each blob image. We have Windows name plus we want to have a distinct Windows name, so we are going to use the index number for this, and then we pass the blob image. Let's check this out. So if we come here, we will have, yep, so we have our original image. We don't really need that. We have the blob 2 and blob 3, and these are the RGB channels of the actual image. I don't want to give you more details on how to like resize or what to really give to the model. For now, it's okay. Just get your image and get the blob of the image and give it to the model. It will work. But if you want to really have an optimized model so that it will detect almost as many possible objects in the image, then you gotta do a little bit more pre-processing on the image and then give it to the model. For now it's okay. So let's stop this back and give this to the network. To do that, we just have something called set input. We get our network and then say set input and then pass the blob. Yep, that's it. To get the outputs, we say network dot forward, which is feed forward, and output layers. Now if you want to know what's in the output, so the outputs, there are a lot of information in the output. Let's check that out. What kind of information do we get? Network output and then outputs. Yep. Let's run this code and see what do we get. Alright, I'm gonna set the visualization false for a while. We don't really need it. And then come here. So if you look at the output, we have a lot of different information, but one thing is for sure, we have an array that consists of 2 more arrays. So let's get them. Let's get the output of each array individually. To do that, we need a for loop. We say for out in outputs, for out in outputs, and then we can print the value of output, but we don't need to. So just this is what you need to follow: detection in out. Well, in each output we have a detection, and that is we gotta get it in that array. And if you want to print the detection, you can just simply see what is in the detection. So we just want to see the value of the detection, and we do it this way. So we don't need to print the output value for now, and that's all. Let's run this code and see what's the result. I think we need to stop that first and then rerun the code. Yep. So yeah, as you can see that, well, basically the how the detection works, it's like kind of template matching. So it has to go through each pixel to find if there is any similarities between what is in the image and what the model knows about the image, and then it gives us a detection. And this is the output for the detection. We have these 5 values, sorry, more than 5 values, but what do we need is to get the score from this detection. We basically go for scores. Let's just write like that. Detection from index 5 up to end. We get all these scores. From index 5 up to end are the scores. And then if you want to print the scores, you'll get some result. Then in each score we have, like, each class has a score. So to find the highest score in that class, we need to get the index of that class. To do that, we just say the class ID is equal to numpy argmax to get the index of that class, and we pass it to we pass the scores into that. Scores. And lastly, we need to find the confidence. Well, what's confidence? I'm gonna come back to that. We have scores and each index that we find before, and that's the confidence. So how the deep learning model works for the classification. We have, let's say, to understand the problem, we break it down to 2 classes rather than 80 classes. Like we have a class of cat and dog. The deep learning model, when it outputs a prediction, it's in a terms of probability from 0 to 1, which is 0 means 0 and 1 means 100%. And then the confidence shows that how confident the network is about the prediction. For example, if there is a dog and the probability that the network produces is 0.7, then it means that the network is 70% sure that this part is a dog on the image, and the 30 other person would probably go for the next class, or it can be discarded based on the number of classes, could be distributed to other classes. So in here, the confidence shows how confident our network is with the prediction, and we set that to be more than 50%. But before we do that, let's just print that out. Confidence. That's it. All right, we don't need that, and we're going to rerun this. So we have confident score. If we just scroll up, you will find some confidence score. So these 0 means these are the areas that the network has 0 confidence that this area would belong to any of those 80 objects. It could be wrong. I mean, there could be an object where the network should have produced a confidence score, but it failed. It means that is the lack of the model. The model couldn't properly classify the object. But for those areas where the confidence is something like 0.1, 0.2, 0.3, then that shows that the network is not very sure if that's an object belong to that 80 class, but still it gives it a confidence that, you know, it could be one of those classes. So we just go down and we will find out there should be like confidences for this for some of the objects in this class. Well, what happened in here is, so as you can see, we get some confidence scores here. 0.2, 0.3, 0.6. So 0.6 means this is a true object that we need for our model. And less than 0.5, we're gonna discard that. We don't really need them. So we set a range. If confidence is greater than 0.5, then if confidence is 0.5, then we gotta get the center of that object, the x coordinate of that object. And to do that, we need to get the integer. So the center, the detection value that I told you before that we are trying to use from afterward the 5th index, like in here. The reason is that before the 5th index, these are dedicated outcome of classes for like kind of dedicated values for the object properties, like the center of the bounding, the center of the object, the width and height of the bounding box of the object, and so on. So if you want to know how these are being understood, you got to go for the data set that the model was trained, like the format, the input format, because that's how we gotta understand that. If you go for the Cocoa dataset input format, you will understand that the first 5 indexes actually dedicated for special purposes. In this case, the first index is for the x coordinate of the center of the object, and we gotta multiply it with the width of the image to denormalize it. So image width, and then we have the center y, and that is detection 1, and we gotta multiply it with the height of the image. So this is the center of the image, and then we need to find the width of the rectangle. So I'm gonna write here rectangle. Sorry, this should be width of the bounding box, and we're gonna change it to detection, to integer, detection index number 3, and then we gotta multiply it by image width, and this is the height of the bounding box, and then we gotta get it in the 4th index and multiply it by image height. So now we can form our rectangle. Yep. So our rectangle consists of the XY position of the rectangle, the starting point, and the width and height of the rectangle. So we have the width and height of the rectangle already. What we need to do is to find the position of x and y. To do that, we need to do a little bit of arithmetic. We have center x multiplied by minus width of the half of the width of the rectangle, and the y is center y minus h divided by 2. In OpenCV, try to have this coordinate in integer value, so we don't want to have problem later on. So just try to make sure that you are using integer to convert that values. That's all. And to collect them into, for each object, we just need to store them in a list. So let's say we have a bounding box, an empty list, and we have, and I'm gonna call this bounding boxes, because bounding boxes. Yep. And then we have class IDs. Well, we're gonna use that to rename our object. Like we gotta give that name to the object, and then we have confidence scores, confidences, and we have class IDs, classes ID. Yep, classes ID. So we come back and then let's add them. So we say bounding boxes dot append and then add this bounding box, which is XYZ width and height. And then we have confidence score, so we add confidence.append, and then we add our confidence score in here. And then we have class IDs, where we append the class ID. Now what we need to do is to, so we the model detects the object for us, and what we need to do to visualize each detected object by putting a bounding box around the object and defining the name of that object using the class ID that we have collected. So we don't need this part for now. I'm gonna comment that out. What we need to do is to to visualize these objects. To do that, we come for the range of the bounding boxes. We come for I in range of bounding box. In range of bounding boxes. To do that, we need to go for the length of the bounding box. Yep. And then we gotta get the label. Okay, let's get the XYZ, W, and H from the bounding boxes that we have defined before, like this. All right, and then we have this label. Well, we get it from the classes that we defined before, and then we have this class ID. So we get each class ID. Yep. So the next thing is we need to do is we need to get the color for each bounding box. So we have a collection of colors. We get them according to class IDs, color. Yep. And then we have this utility function from CV2 that draws a rectangle. We give it to the original image. We pass the starting and the starting XY coordinate of the rectangle, and then we drive the rectangle by X plus W, the height and the width and the height, and Y plus H, and then we give it a color and then the thickness, and then define the we're writing the name of the name of the detected object onto the image. So we use the image label and XY. Let's give it like 30% above the bounding box, and we can see the font that we defined before, and we gotta pass the color and the thickness. And if we show the image back, we'll get the actual image with the bounding boxes. So let's check this out. Well, there is one thing we try to define. We need to turn on this debug to true so that we can visualize it. So we got a problem in here, and that's called font scale. Well, let's see what's the problem. We have CV2 font. Alright, I think that we put something, we missed to put the skull in here, and that should work now. We give it a scale, and let's see. Yep, let's see the image. There we go. We detected the objects on the image, but as you can see, there's a problem. The network is kind of like detecting so many bounding boxes for the same object. Like in here we have like around 8 or 7 bounding boxes for the person and so many bounding boxes for the cars. We don't want to do that. In order to avoid that, there is a very nice algorithm. Whenever you face such a problem, you just need to go for something called non-maximum bounding box repression. Non-maximum suppression bounding boxes. So that's also available in the DNN module. All we need to do is to pass this confidence score to the non-maximum suppression bounding boxes, and then it will gives us the only bounding box that is that has the highest confidence. So to do that, we just need to come here and say indices and say cv2.dnn and non-maximum bounding boxes, and then we gotta give that bounding boxes in here that we found before, and then the confidence, and we have a threshold and threshold. That's it. So if you want to know more about the non-maximum bounding boxes, check out the link below. I have provided a little bit of description about non-maximum bounding boxes. Go there and read about it. It's a very cool algorithm. And then what you need to do is to check if I that we found there is in the range, is in the indices. Then do all this operation. So that's it. Let's check out again. Can't convert vector element for scores index 0. Well, let's see where is the problem. CV2 NMS boxes, and if NMS is in that range, try to get the bounding box in this for scores index 0. So let's check this again. Can't convert vector element for scores, so we need to convert this to float. It does not get the integer element, and then let's check it again. let's see our result, and there we go. The final output of the images, we have the bicycle, we have the number of cars, and we have the person and track. If you want to know how many objects have been detected, basically just do this: print the size of the confidence score, number of objects detected, and then the length of confidence, and it should gives us the number of objects that has been detected in that specific image. So 28 object. Well, it's not 28 object because there are number of bounding boxes that has been duplicated. So to exactly know how many object has been detected, we need to check the final output in here. For I in indices, all we need to do is to I, we can say I print I. Hold a second, we need to print the size of the indices. Print if number of objects detected distinctively. How many objects we have detected? We can see that by checking the length of indices. So we try to remove the duplicated objects. We have 9 objects detected in this picture. So if we counted 1, 2, 3, 4, 5, 6, 7,